Yeah, good morning, and thank you already for joining our webinar today on how to avoid common mishaps in your daily work in your laboratories. And thanks again for joining today. Before we will start this session, just share with you a couple of housekeeping notes. You don't have to write anything down or make some notes or some in that direction, as we will share all materials in this webinar, including the presentation from Sasha, in a follow-up mail which we are sending quite after a couple of minutes after the webinar together with a small survey. So if you have any questions, don't hesitate to ask them. We will take care about them in parallel to Sasha's presentation. And how to do that, it's just click on the question mark icon on the top of your screen and raise your questions whenever you have the feeling, oh, this I have to know, or this I have to ask. So we will take care about all your questions. The recording as well as the materials, as I said before in a way, will be sent out in our follow-up meeting. Having said that, I hand over to Sasha Kunkel from the company Asecos. The stage is yours, Sasha, and thanks for giving us the insights today.
Sure. Thanks, Frank, and welcome everyone to this webinar today. My name is Sasha Kunkel. I'm Vice President of Global Markets at Asecos. Today, we will address the risks and potential accidents we typically see in the laboratory setting with a special emphasis on fire and explosion hazards. Awareness is key, or as we say in German, Gefahr erkannt, Gefahr gebannt, which simply means once you recognize the danger, you can take effective measures to mitigate it. A few examples of accidents that made the headlines in Europe in recent years. University of Southampton, UK, a postdoctoral researcher got injured by improper handling of a highly reactive chemical. Another one at the Eidgenössische Technische Hochschule in Zurich, Switzerland, in 2014, an explosion involving flammable gases. Then Karolinska Institute, Sweden, again, mishandling of chemicals. 2018, University of Leiden, Netherlands, improper handling of flammable chemicals. Bordeaux, France, mishandling of explosive materials. And then again in Bristol, UK in 2019, another improper storage of chemicals leading to a fire in the chemistry lab. I could go on and on and on. The true number of lab accidents occurring in a year can vary significantly. That depends a lot on the country itself, the safety culture, right? But also the type of lab. So whether it's an academia lab or industrial or a research facility, and not to mention that many accidents don't get reported at all, right? So whenever possible, the institutions try to keep things quiet. Yeah, this is nothing to be proud of. However, we could find some general statistics then that can provide us with the rough estimates. In the US, for instance, the OSHA and other sources, they indicate that thousands of lab-related accidents happen annually. For instance, there was a study in the Journal of Chemical Health and Safety in 2015. They noted about 1,000 accidents reported over a 5-year period in academia alone. Another report from the American Chemical Society indicated that nearly 10,000 lab accidents were reported in academia alone over a 5-year span. So that would make around 2,000 accidents per year on average. And on a global scale, getting a precise number is even harder, if not impossible. So estimates suggest that we are talking about 10,000s of accidents worldwide. But in the end, the exact number doesn't matter, right? That's just statistics. What does matter is that accidents do happen all the time, and we can greatly tilt the odds in our favor. The important accident is the one in our lab, right? We don't want an accident in our lab. And we can do that by adopting a robust safety culture. And this is really what we want to explore today. Allow me a few very short words about who we are and what we do. Asecos stands for Approved Safety and Ecology Solutions, and we specialize in the safe storage of hazardous materials indoors. Our headquarters and factory, as you can see on this picture, is located in Gründau. That is a small industrial town close to Frankfurt am Main in the center of Germany. We have group companies in the Netherlands, France, Spain, UK, Switzerland, Sweden, and the United States. And we currently employ about 400 employees. We specialize in safety storage cabinets. And that was, in fact, the original idea of our founders to develop a 90-minute fire-resistant cabinet for flammables. In 1994, they made this vision come true, but a lot has happened since, of course. So today we provide more than 250 different models with many thousands of interior configurations. But the basic idea is still the same: to contain hazardous materials safely and to protect the stuff that handles these substances. Now let's take a look at the most common bad habits we see in laboratories today. And this list here is by no means exhaustive, right? There are many more, and many of them are very closely related, right? I will address them one by one today with a special focus on our area of expertise, meaning hazardous materials, and even more specifically, the flammable materials. And as you quickly notice, they touch on many, if not all, of these bad habits. First one, failure to wear PPE, so personal protective equipment. That should be blatantly obvious, but we see it all the time. Yeah? Ignoring or improperly using PPE, such as the gloves or lab coats, goggles, respirators. This bad habit increases, on one hand, the risk of exposure to hazardous materials, biological agents, physical hazards also, and it's also really our last line of defense if all other protections fail. If you've been to one of our previous talks, you might have heard of the STOP principle, the STOP principle. STOP is a very powerful tool that can help us with our risk assessments, right? So when we see a risk, it helps us to really address this risk and come up with effective measures to mitigate that risk. I will explain it briefly. STOP stands for substitution, technical measures, organizational measures, and personal measures. So, and it's hierarchical, right? So we should start with the substitution. So when we look at hazardous material, we should first try to get rid of it, right? The best thing would be we could substitute this hazardous material by a non-hazardous material. If we can do that, perfect. Yeah, we don't need our risk assessment any longer. There's no risk anymore. But chances are that we need that hazardous material for our process. So the next question would be, can we maybe use a less dangerous material? Yeah, so maybe a material with a higher flash point. What that means, I will allude to later on. Or maybe we could rather than having big containers coming in, let's say once a month, maybe we can have smaller containers coming in every week, right? So that we reduce the quantity. So that would all mean substitution. Once we've done that, we can look at technical measures. Technical measures simply means how can we house the danger, right? So looking at storage, this could be a safety storage cabinet. Or when we look at handling hazardous materials, the fume hood would be the perfect technical solution to manage that danger. If we can't do that, or maybe that is not enough, right, then we can look at the organizational measures. That means we limit the exposure to that hazardous material either time-wise or space-wise. Yeah, so for instance, we could say you can only use that material for 5 minutes a day, or you have to keep a certain distance. But you already realize probably that this depends a lot on the compliance of the person, right? And we are all human, so we have good days, we have bad days. It's not a perfect solution, right? So whenever we can take the human element out of the picture, it's generally a good idea, right? So the technical measures should always take precedent over the organizational measure. And then the last one, that's our PPE, our personal protective equipment, the last line of defense, as I said, yeah. So that would be our gloves, our goggles, and so on. Yeah, should be a no-brainer, but we see it all the time, right? Over time, we become a bit complacent, maybe a little overconfident, and that's when things go wrong. I've seen it myself sometimes when I visit a lab, it's just a brief visit. You just want to take a look at a cabinet or something. I had it many times, where they say, don't worry about the lab coat. You're in there just for 2 minutes. Well, still, it's only 2 minutes, but let's take that little extra time to wear our lab coat. Second bad habit, poor housekeeping. That's, of course, a very broad statement, right? It can mean neglecting to clean workspaces, for instance, or to clean equipment, glassware, yeah? And that would eventually lead to contamination. But it can also mean handling or storing hazardous material improperly. Yeah? So specifically, use your fume hood and safety storage cabinet. So a bottle or a container should never be out in the open unless it is in use. And if it's not in use, put it back into the safety storage cabinet. And that includes the fume hood, right? So you see in that picture, a fume hood is for handling hazardous materials. It's not for storing, right? So the moment you're done, the flammable material or the hazardous material should go out of the fume hood. Inadequate storage can also mean, for instance, improper labeling, yeah, or not labeling at all. It can also mean overcrowded storage. Yeah, so you have a safety cabinet, you run out of space, but rather than get another one, you start stacking the chemicals. Or incompatible storage, right? Putting chemicals that maybe have a tendency to react with each other closely together. So that's all things to pay attention and fall under the category of poor housekeeping. I mentioned before that Asseco's offers more than 200 different models and many different interior configurations, yeah, safety storage cabinets. So that can be quite confusing, right? And different hazardous materials have different dangerous properties. So flammable materials, for instance, they need to be kept in a fire-resistant cabinet because the danger potential here is having a fire or an explosion. So that is the key danger. For a corrosive material, on the other hand, the flammability is not the problem. The problem is we need a corrosion-resistant construction. We need powerful extraction systems, right? Or for toxic substances or gases, other factors are critical to observe. Now, the sheer variety of cabinets can be confusing. So we at Assecos and our friends at VWR, they're very happy to assist you to find out what is the right cabinet, the right configuration for you. You can also utilize our configurator on the website that can help you find the right solution. And we also offer frequent trainings, such as this one, in our Assecos Academy. So that is our training platform, both on and offline. And you might find interesting as well. The next one on our list, ignoring safety protocols. That goes very much hand in hand with our previous one. So safety protocols, that could again mean handling and storage procedures for hazardous material, but it can also mean operating guidelines for equipment. It could mean maintenance schedules, calibration procedures. Yeah, so and this bad habit is a really tough one because often that is intentional, right? And the only way to overcome this is frequent training, yeah, and making people aware that what their negligence can cause. Yeah, this must always be personal. People must be able to relate. Yeah? If they don't feel that it could be them creating the accident and them feeling the repercussions after the accident, they might not really internalize the safety protocols. Yeah, so repetition is the mother of all skill, as we know. So training, that is really the best way to overcome this bad habit. Number 4, improper chemical handling and storage, and more specifically, hazardous material. And that is really our domain. And unfortunately, this is the bad habit that often leads to the worst accidents. I will delve quite deeply into this part. So we start basic. What is a hazardous material? Hazardous material is any item or agent that has the potential to cause harm to humans, animals, or the environment, either by itself or through interacting with other factors. A hazardous material can be a raw material, crude oil as an example. It can be a finished product, so let's say petrol that was made out of that crude oil, but it's also the waste materials. And that is an area that often gets overlooked. This is an area that we address later on. That's actually one of our bad habits. I believe it's number 7 or 8, the waste materials. For now, let's just remember hazardous material, raw materials, products, waste materials. And how can we tell that we are dealing with a hazardous material? Well, the most obvious thing is the label, the pictogram we see. Here you can see 9 hazard pictograms. They are according to the GHS, the globally harmonized system of classification and labeling of chemicals. GHS was introduced in 2012, and for the first time ever, we had a global approach, right? Before that, it was very confusing. Every country, every region had their own ideas, their own symbols. Some of you might remember in Germany, we had those orange symbols. But again, it's the past. We did it in 2012. I think it took us 25 years or something like that from the idea till finally implementation. But now all you need to remember is those 9 distinct symbols. Yeah, all the transition periods are over. So if you see bottles still in use that carry other symbols, chances are they're old bottles, so they need to change. Yeah, we cannot use those old symbols. I will run through them very briefly. I'm sure you're all familiar with them. At the very left, you have the environmentally dangerous substances, then the gas cylinders, the health hazards, the oxidizing materials, the flammable materials in the very center, the toxic materials, the corrosive materials, irritants, and on the very right, it's the explosive materials. Of all those hazardous materials, the flammable materials, they rank first, by far, when it comes to accidents in the labs. Why is that? Let's delve a bit deeper. Flammable materials can lead to 2 bad outcomes. The first one is a fire. A fire is not necessarily a big problem, right? If it's a small localized fire, there's not much flammable material around, you realize it immediately, you might have your fire extinguisher nearby, you can deal with it, you can put it out. What's much more of an issue, and that is our second possible outcome, that's the explosion. And explosion are very hard or if almost impossible to really control or contain. So our best bet here is really to prevent the explosion in the first place. And how do we do that? To prevent an explosion, we need to first understand the underlying causes, right? So what needs to happen to create an explosion? The fire triangle you see here is really a great tool to memorize that. Fire triangle shows you the 3 conditions that you need in order to create an explosion. The first corner of the triangle or side of the triangle is the flammable substance. That's common sense. Yeah? It can be a gas, a liquid, or a solid. Typically, the flammable liquids are the biggest group of flammables. Yeah? So, of course, there's exceptions, like when you're a gas manufacturer, then probably gases is your number one. But by and large, if you look across the entire industry, the flammable liquids are by far the biggest group. Also in the lab, that's typically your biggest flammable substance. Then the second element we need is oxygen. Oxygen is in the air around us, about 21% nowadays. We humans, we don't do so well without oxygen, right? So when the concentration drops down to about 15%, we can function pretty normal. If we do something laborious, we might feel a little bit more exhausted. Yeah, we breathe a bit more, but still no big deal. But then once it goes down to 12% and definitely sub 10%, it becomes very dangerous and eventually fatal. So in every lab, we have oxygen, unless it's something very special. We wear breathing equipment and everything. So in most regular cases, we have the oxygen. So we have already 2 conditions present, the flammable substance, the oxygen. So all we need now is an ignition source, and that is our third component on the left. Ignition sources, there are 13 in total. I have put down the most common ones here that we see in pretty much every laboratory or work area. The first one, the open flame, that's very straightforward. Yeah, that could be your Bunsen burner. It could also be a light. So everything that creates an open flame. Open flames, depending on the chemical, sometimes they're barely visible. Yeah, so methanol is one example. Yeah, it burns with a very blue flame. So sometimes it's very, very hard to see that there is actually an open flame. Mechanical spark and electrical spark are the next on our list. Mechanical sparks, typical situation is when you use a saw and you cut stone, for instance. You see all these mechanical sparks, or welding. You see the mechanical sparks. Very effective ignition source. The next one, electrical spark. Electrical sparks can be caused by every electronic device that is not specially protected. Yeah, you might have heard of ATEX, yeah, the ATEX regulation. So of course, it's possible to design electric appliances that they are intrinsically safe, yeah, that they cannot serve as an ignition source. But our typical devices, they are not specially protected. There are sparks. You can see that when you pull a plug or when you flick a light switch, there's a spark. Sometimes you even see it. Very powerful ignition source, right? So if there's an explosive atmosphere present, it will ignite. Next one on our list is the chemical reaction. Chemical reaction, that simply means we have two or more substances that are incompatible, that react with each other in an exothermic fashion, meaning creating heat and eventually ignition. The next one, the electrostatic discharge. We have all witnessed that, I suppose. Yeah? When we were kids, it was good fun, yeah, to go on a carpet with our rubber shoes, yeah, get electrostatically charged, and then shock our friends. Still good fun today, to be honest. But joking aside, this is quite a common ignition source we have in labs. Where do we see that? Typical situation is decanting from a bigger container into a smaller container. Okay, this is a situation where static electricity can start to build up, and if we don't follow the proper grounding protocols, yeah, so to connect the containers and ourselves to Earth, we could get a build-up of electrostatic charge, and that then leads to the discharge, so spark. Next thing is maybe a small ignition, small explosion, and then when we have more flammables around, it can very quickly lead to a very, very dangerous situation. YouTube is full of examples, so feel free to look for it. So it's something that we unfortunately can see quite a lot. The last one here, hot surface. Again, that's a classic one in the lab. The hot plate, as we have seen in this short video clip at the beginning, when you get a splash on the hot plate of a flammable substance, you get immediate ignition. It could also be a forklift truck in a warehouse, for instance, where the engine runs hot and you get a splash of, let's say, petrol or acetone or whatever on it. So those are really the most common ones. There are some more exotic ones, radioactivity and so on, but this is more, let's call it exotic. But those 6 ones here you will find in many laboratories and workrooms. So to prevent the explosion, all we need to do is basically take one out of the equation and we prevent it. Once again, getting rid of the flammable substance, it would be great, but not really doable in most cases. Same goes for the oxygen. So all we can manipulate is the ignition sources. So think safety storage cabinet. One of the main features is to shield the ignition sources from the stored flammable materials. Another very important term to remember here is the flash point. What's the flash point of a flammable liquid? The flash point is the lowest temperature where vapors of a flammable liquid start to form and then can be ignited by a separate ignition source. It may sound a little bit complicated, but it's actually quite straightforward. I like to show you a little video at this point. The first experiment here will involve an extremely flammable liquid with a very low flash point. Petrol, ordinary petrol we use in the car, flash point minus 20 degrees, even a bit less. So even on a very cold winter day, it is still flammable. Let's find out. We use an open flame and it ignites instantly, right? What we can also see nicely here is that it's the vapors that are burning. It's not the liquid itself. So the term flammable liquid is even a little bit misleading. Now let's repeat our experiment with another flammable liquid, this time with a very high flash point. Okay, the petrol had a low flash point, minus 20 degrees, so much lower than ambient temperature. This one here has 40 degrees Celsius, so much higher than ambient temperature. And according to the flash point definition, no fumes, no ignition. And that's what happens. So one could imagine, or one could think, okay, this is not very dangerous, right? We don't need to handle or store that in a special way. But think about it for a second. What happens when the temperature goes up? Yeah, so let's assume we have a fire somewhere close by in our lab. The ambient temperature rises, and in turn, the temperature of the liquid goes up. That's what we simulate here on this hot plate. Temperature starts to rise. We are now at around 30 degrees, so still nothing, okay? And then as soon as we reach our flash point, so the 40 degrees in this case, the liquid starts to create fumes, and it acts just like any other extremely flammable liquid. So when we handle these substances, it's true that the ones with the higher flash points are less dangerous than the ones with the lower flash point. But in a storage situation, we should consider everything as potentially highly flammable, because it would all make the fire worse. It would all fuel a pre-existing fire more. The classification of flammable liquids according to GHS, you can see it here. The highly and extremely flammables, they have flash points of less than 23 degrees, so less than room temperature, less than ambient temperature, right? That would be category 1 and 2 according to GHS. And then we have the flammable liquids. They have flash points from 23 up to 60 degrees. So those would be the flammables. They all carry the flame symbol, right? So just by the symbol, you cannot distinguish between highly, extremely flammable and flammable. But for our purpose, it doesn't really matter. When we think of storing, we should consider everything as potentially highly flammable, put it all in a safety storage cabinet, and you don't have to worry about it. A few examples of commonly used flammable, extremely highly flammable liquids. Again, you see the petrol here, minus 20 degrees, so very low flash point. But it also means, imagine you're in a very, very cold place, right? Somewhere up north, maybe the north of Norway or so, where you get to winter temperatures of minus 40. Minus 40, if you have a petrol-driven car, your car won't start, precisely because of that, because it doesn't create fumes, too cold, right? We are below that flash point. At the bottom, you see the paraffin oil with the flash point that was 40 degrees, depends a little bit on the type of paraffin oil, was not flammable at room temperature, but it became flammable once the temperature goes up. Now, there's one more important definition, and then we move on, and that is the auto-ignition point or the self-ignition point. Now, what's that? Self-ignition point is simply the lowest temperature where those vapors would start to self-ignite. Okay, so we no longer need a separate ignition sources. So to give you an example, the petrol, auto-ignition point about 250. Take a look at the flash points and the auto-ignition points of these examples here. You see that there's no correlation, right? We cannot just say the lower the flash point, the lower the auto-ignition point. It's actually oftentimes the opposite. A good example is the acetone. Acetone, very common solvent, very low flash point. So clearly an extremely flammable liquid, but it has a fairly high auto-ignition point. And the paraffin oil that wasn't even flammable at room temperature would be the first of all these substances here that would start to self-ignite when we have a pre-existing fire. But once again, it's not so important to memorize all these different numbers. What matters is put those flammable liquids in a safety storage cabinet. You don't have to worry. Because the second important feature of a storage cabinet, a state-of-the-art storage cabinet, is to keep the temperature below self-ignition, so below 200 degrees effectively over 90 minutes of time, so 1.5 hours. So that's the second important aspect of such a storage cabinet. Back to the danger triangle or the fire triangle, quantities matter, of course, right? So there is basically a fourth corner of that triangle, and that is the mixing ratio or the concentration. So if I put a tiny amount of petrol in a large room and I have oxygen and I have an open flame, nothing will happen, right? Because the quantity is just too small. But what is a dangerous quantity? Or is there actually is there a threshold? Is there that magic line? Can we say up to, I don't know, 10 liters or 20 liters, 50 liters, it's completely harmless, and then a little bit more, it becomes a problem? You already hear probably how I say it, that this is not possible, right? There is no clear threshold. But let's take a look and maybe quantify that a bit better. Another short video. In this case, we are using lab bottles. So those are empty 500 milliliter lab bottles. And we are now trying to find out how much of a flammable liquid is necessary to create an explosive concentration inside this half-liter bottle. First, we will use one single drop of our petrol. So same petrol we used before. It's an extremely flammable liquid. It has vaporized, so you won't see any liquid in here. Our ignition source will be a hot surface, so that device glows at the end. And as you can see, you see nothing at all. So obviously one single drop in a 500 ml bottle is not enough. So second experiment, we will use a bit more. This time, my colleague here will use 5 drops of petrol. One, two, three, 4, and 5. We will close the bottle and also shake it a little bit, so that we get a mix. You will still not see any liquid, so this bottle, just as the first one, appears to be empty. Let's see if it is empty. And this time we get an explosion. When we do that live, you would be quite surprised how powerful that little explosion actually is. Third experiment, this time we take more. Okay, so this time we use 100 drops, so what is that, 10 milliliters, 5 milliliters maybe, considerable, right? You can even see the liquid this time. So probably the bigger the quantity, the bigger the explosion, right? Is that what we learn here? Let's find out. And to our surprise, no explosion at all. There's just a small flame on top of the bottle. What we have seen here was a demonstration of the explosion limits. Flammable liquids and gases have explosion limits. In the first experiment, where we used one single drop in a 500 milliliter bottle, we had a so-called lean mixture. There was simply not enough fuel inside to become explosive. In the second experiment, with the 5 drops, we were exactly in the right range. We were above the lower explosion limit and below the upper explosion limit. And this is really where it's dangerous. And then in the third experiment, where we used 50 drops, 100 drops, we could in fact pour the entire bottle inside and we would still have the same result. It's a rich mixture, a saturated mixture. It is no longer explosive, but it is flammable at the very top where it mixes with air. But how can we deal with that? How can we prevent those explosive concentration? The answer is technical ventilation, right? If you ensure at least tenfold air exchange within your storage cabinet, or within your storeroom, you will never reach an explosive concentration. We will never get above the lower explosion limit of that flammable substance. But ventilation is not only important to prevent explosion, it is also critical to safeguard our health. The last thing we want is to chronically or acutely inhale chemical fumes. And as a matter of fact, if you compare the lower explosion limits and the occupational exposure limits, so the concentration that start to get dangerous for your health, you're in for a little surprise as well, because the occupational exposure limits, they are much lower than the lower explosion limits. So the health risk is actually present long before you have to worry about explosions. So let me give you one example: acetonitrile. Acetonitrile, one of the most common flammable liquids in the lab, I suppose. The legal airborne permissible exposure limit, according to OSHA, is 40 parts per million, so 40 ppm over an 8-hour work shift. The lower explosion limit of that substance, of the acetonitrile, is 44,000 parts per million. So it's several thousand-fold higher. So that's why we advocate for technical extraction, always, regardless of the type of hazardous material you're storing. The investment is comparatively small. You do that one time, do it right one time, and you don't have to worry about lower explosion limits, about occupational exposure limits. Whatever is in your cabinet will not harm you. Next bad habit, taking shortcuts. And I'm sure that we have all been guilty of that at times. I definitely have. It can mean rushing through procedures or skipping steps to save time. And that, of course, increases the likelihood of errors. It makes things more inaccurate, and it also presents big safety hazards. Examples could again be not using PPE to save time. Coming back to my example, visiting a lab, or maybe I forgot something, right? I'm done, and I forgot something. I just briefly go back to catch it. Yes, but put on the lab coat. And again, this is a tough one to tackle because everything nowadays is geared towards more efficiency. So oftentimes there is a strong incentive to take shortcuts. Anyway, fight that urge. Don't do it. Take the appropriate time. Efficiency is not everything. Sometimes a little bit of inefficiency is probably a good idea. Number 6, ignoring equipment maintenance. Neglecting to perform routine maintenance or calibration, safety checks, that can lead to malfunction or inaccuracies again, but it also creates safety risks. So that sounds pretty straightforward. Again, I mean, I don't think you learned something entirely new today, right? But it is important. It just gets overlooked at times. So check the required maintenance intervals of your devices. Make sure you have safety contracts in place, and that is true for your fume hoods. It's true for the safety storage cabinets, for filtration systems. So to maintain the protective functions, all these systems really have to be serviced at least on an annual basis. Filtration systems, typically they have saturation monitors. So depending on the load, you might have more frequent service intervals. So it's very, very important to observe that correctly. It is a cost, of course, but again, it's important to prevent inaccuracies and also accidents. Next in line, using equipment or procedures, using incorrect equipment or procedures. So that could be a wrong type of pipette, or it could mean we use we centrifuge the samples at the wrong speed. So that can, best case, lead to experimental errors and unreliable results. But as I said, best case, it can also have dire health consequences. For instance, operating a fume hood improperly, that can lead to very bad scenarios. Fume hoods were designed for 4 things: capture, contain, dilute, and exhaust. But in our efforts to save energy, the dilution oftentimes gets a bit overlooked. So many hoods are operated at minimum airspeeds. That's obviously great to save energy. It's good for the environment, but it also means that the system is much less forgiving when used improperly. So you could potentially be exposed to chemical or biological agent. What is also a very worrisome trend that we see recently is using non-original equipment, knockoffs in plain English, to save costs. And this is particularly dangerous when it comes to batteries and chargers. We see more and more fires and explosions also in the labs resulting from battery-driven devices, from lithium-ion battery-powered devices. There is a reason why you can buy these cheap knockoffs at such a low price. So when you have battery-operated lab equipment, really make sure that you only use original batteries and original chargers. And this is also a good idea for the personal devices you might bring into the labs. Yeah, think phones, tablets, laptops, or maybe even micromobility, right? So maybe you bring your scooter to work. So don't fall for the allure of that cheap product on the web. Spend a bit more and go for the original, the original batteries, the original chargers. Number 8, another big one. I touched on it briefly before. Improper waste disposal procedures. When you improperly dispose chemical, biological, or radioactive waste, yeah, so maybe pouring hazardous material down the sink, yeah, or failure to segregate them properly, that creates big risk both for the environment, but also again a big safety risk. It doesn't stop at the waste level. Yeah, so pun intended. I mentioned that before on the hazardous materials slide. Waste material is so often overlooked. Yeah, look at this picture, for instance. Yeah, state-of-the-art installation of fume cupboards. Yeah, the best and safest you can get, but underneath the fume hoods, nothing. Right, the waste got completely overlooked. There's no cabinets, nothing that contains, nothing that shields from ignition sources, nothing that extracts potential explosive concentration. So we often see safety protocols in place for handling, for storing. What about the hazardous materials coming in? We learn what we can take in an elevator or what we cannot. But the safety protocols when it comes to waste, oftentimes non-existent or really there's much room for improvement. It's possible to use safe systems. Yeah, they are available. We do some of them. We are not the only ones. Yeah, so when you think of safe liquid waste collection, yeah, five important points to address. First one, fire protection. Yeah, so it needs to be shielded from the ignition sources. Next one, electrical conductivity. Think flame triangle, fire triangle. Yeah, we don't want static electricity and ultimately electrostatic discharge. We have the material resistance that matter. Yeah, so depending on the solvent you use, or maybe it's a corrosive material, so that's an important aspect. And then also monitoring capabilities. For instance, we don't want our container to overflow. And then the fifth one is extraction. Yeah, we never want explosive concentration, and we also don't want to create any health risk for us. So if liquid waste collection is an area of concern for you, please get in touch with your VWR representative. They will be happy to point you in the right direction. The next one, number 9, that should be a no-brainer again. Don't eat or drink in the laboratory. Consuming food or beverages in the labs, it increases the risk of contamination and exposure to hazardous substances. And worst case, direct ingestion of harmful chemicals or biological agents. It sounds simple, and yet we have seen many grisly accidents happening. I remember one very clearly. It was the standard story of a professor at the former BG Chemie. That's the German Employers Accident Insurance Association for the chemical industry. He always told that in his safety trainings. And the story goes pretty much like that. It was not in a lab, it was in a factory, but it could have just as well happened in a lab. It was a hot, sunny day. So the worker was working for quite a while, was pretty thirsty. Finally, there was a break, and he wanted to drink from a Fanta bottle, from a lemonade bottle. He took it, and because he was very thirsty, he took a couple of big gulps before he realized that it wasn't lemonade in this bottle. It was actually drain cleaner. Okay, so it was sodium hydroxide. Unfortunately, or without going into too much of the ugly details, suffice it to say that he was admitted to the ICU very shortly afterwards, where he spent 7 days in agonizing pain before he was passing away. There was nothing the doctors could do, except trying to reduce the suffering. His esophagus, his stomach, everything had literally starting to dissolve. So drain cleaner, again, it contains sodium hydroxide, which is an alkali. Okay, it's not an acid, it's an alkali, and it has a very strong irritating and corrosive effect on the eyes, on our skin, and also to all mucous membranes. Yeah, okay, mouth, yeah, the entire intestinal tract. And even concentrations as low as 1% can already cause big harm. And then higher concentration, they lead to deep necrosis, known as liquefaction necrosis. So that's what happened to this poor devil. And burns from alkaline substances, they are harder to treat than burns caused by acids, because exposure is often not detected so quickly. Yeah, it has a delayed effect. And also alkalis, they are very hard to remove. They don't mix well with water. Yeah, so it's both acids and alkalis cause bad effects, but the effects can be very different. I want to show you a final video here showing that. I know we cover a lot today, but let me show you this one. First one involves an alkali. That's again, it's that very sodium hydroxide that is part of the drain cleaner that yeah, this poor guy used. And we pour a bit in this dish. It's a 20% solution, so 20% sodium hydroxide. Our tissue sample will be a chicken egg, and we dump the chicken egg into the alkali. Give it a couple of seconds to react, and let's see what happens. You can see it starts to liquefy. We can see that necrosis starting to happen. So imagine you had exposure to a mucous membrane. Second one, this time acid, highly concentrated acid, sulfuric acid. Same experiment, we pour a bit in this container. And once again, our tissue sample here will be a chicken egg. Let's give it a few seconds. We get a chemical burn, but a different one. You see, this time the egg kind of chemically cooks, okay? There's also heat generation. You can see the temperature rises a little bit. And what you can also see now, this dark substance that is settling down, that's the actual carbon that gets pulled out of the egg. Okay, so two different ways of causing the chemical burn, but both of them are very, very bad. So eating or drinking in the lab, just don't do it. And our final bad habit, failure to document procedures and results. Neglecting to document experimental procedures or observations, and then to capture the results of our experiments accurately and comprehensively, that can lead to all kind of bad things. Data loss, issues reproducing that particular experiment, difficulties interpreting the results. But yeah, it's also true for risk assessments, for instance, or for safety data sheets. Risk assessments, they must be done frequently. Yeah, so we have to review them frequently. So whenever something changes, our materials change, our processes change, our devices, our configurations change, personnel changes, right? We might get new, maybe a little unexperienced personnel. So then we always have to review and update our risk assessments. And the same is also true for our safety data sheets. Safety data sheets, make sure you have the latest ones, make sure that your lab personnel is familiar with them, and make sure that they're easily accessible. Sometimes when we do our trainings and we ask, where do you keep your safety data sheets? We get the answer, electronically or on the internet. Yes, of course, you have them on the internet, But the last thing you probably want to do is when you have a chemical spill in your eye, is to go on Google and look for chemical spill. Right, so it's very important that you have them close by, have them as a paper copy, or at least somewhere, on a tablet or something that is easily and quickly accessible, and doesn't require any logins or internet connections or whatsoever. And make sure to update them frequently. As we learned, the GHS symbol, they came in 2012-ish. So if you have an old safety data sheet that predates that, chances are that there's different symbols on it, so you might not be able to find the answers you're looking for. Before we finish our session today, let's turn those bad habits into good ones, and that should really be the takeaway for today. I will read them out loud. Nobody's perfect, right? But if our actions can prevent just one single accident, I think it was already a success. So let's start with the first one. Always wear your personal protective equipment. Wear your PPE, even if it's something very short. Put on your glasses, put on your safety coat, etc. Proper housekeeping. Prepare properly, clean up properly. Follow the safety protocols. So read your operational manual. I mean, I'm guilty of that too, right? You get something new, you start immediately using it. It's a good idea to take a moment, familiarize yourself with the operation manual. And again, training. Repetition is the mother of all skill. I don't tire to repeat that. So make sure you have frequent updates. Safe chemical handling and storage, very comprising topic. There's very many courses out there that you can use. Many of them are free. We do many of them, so make sure to do that on an ongoing basis. Don't take shortcuts. Just don't do it. Efficiency, not always the best idea, especially not when it comes to safety. Keep your equipment well maintained and serviced. There's a cost to it, yes, but an accident will definitely cost you more. Use always the correct equipment and procedure. Don't buy cheap knockoff versions on the internet. Follow your waste disposal procedures properly. Never eat or drink in the laboratory, ever. And document your procedures and results carefully. And that's it. Short and sweet. Thank you very much for attending our today's session. I hope it was insightful to you, and I believe we have some time left. So I would hand it back at this point to Frank, and let's see if we have any questions.
Yeah, thanks, Sasha. And that is, wow, that was quite impressive. And you reached that target, making me feel very bad about drinking and eating in the lab. I remember my lab times, 30 years ago, where such safety rules were not really in place. So fully agree what you stated. And I just checking the question area. We got a couple of, but they were answered. But it would have surprised me if any question is left, because your presentation was really, really good. But I'm sure questions will arise. That's for sure in the day-to-day work for our customers and participants. And if so, and if that's the case, don't hesitate to write a mail to webinar@avantrosciences.com or contact your local Avantro sales representative or our colleagues from ASECO's either. We are there to help you and happy to help you to select the right cabinets or to give you guidance on everything what Sasha introduced us in this call today. And just give a couple of seconds if there are any additional questions, Sasha. Okay, that seems to be not the case, Sasha. Thanks all participants for joining us today. As said before in the housekeeping notes, we will send out the recordings quite soon after the webinar together with a small survey. So would be great if you can share your feedback on this impressive presentation with us. That gives us then the confidence to proceed with those kind of webinars also in the near future. And thanks again. Have a good rest of the day and a safe rest of the day in particular. And thanks, Sasha, again for your contribution to today's webinars.
My pleasure. Thanks a lot,
Yep.
everyone.
Thank
Take
you.
care.
Bye.
All the best.
Cheers. All the best. Yeah. Ciao.